Welcome to the lecture on phase diagram of non-ferrous metals and alloys. So, in the last lecture we discussed about the phase diagram of ferrous based system, especially iron carbon phase diagram. Now, we will also talk about some of the important non-ferrous based materials phase diagram. So, coming to first case, that is of the isomorphous system, and this is of the copper nickel system. So, isomorphous binary system, that is we have already seen in our earlier lectures that isomorphous system is the one where you have complete liquid as well as the solid solubility. And what you see is that you can see that you have on this side you have copper, and this side you have 100% nickel. So, copper has the melting point of say suppose 1083 degree centigrade, and it is higher. So, that way, and what you see in this case that you have, this is your FCCC solid solution alpha, which is there below this line, and above the liquidous line you have all liquid, and in between you have liquid plus alpha zone. So, again when you come to this liquid plus alpha zone, in that case you can use these tie line rule and the lever rule to find the percentage of the liquid or the alpha in such cases. So, suppose you have to go to any intermediate temperature. So, if you so in these cases, as you know, that if you come to such system, so you have seen that this is how one isomorphous binary system will look like. Now, if you are so you will have liquid here, this side you have alpha, and this is your liquid plus alpha. So, if you come to any when the temperature is reached to this, up to this point there is no solid formation. After that you will have the solid formation, and suppose so in this zone you will have only the liquid, and when you come in this zone you will have liquid as well as at some places you will have solid crystals formation, and the solid which is formed, it will be basically based on this composition, and the liquid which is formed is so solid will be on this composition and liquid will be of this composition. And if you come to for any particular line, then the amount of solid formed will be this upon this, and similarly amount of liquid formed will be this upon this. So, that is the fraction of the solid or the liquid which is calculated based on the tie line rule and the lever rule. So, if suppose so this is normally you have the either copper nickel system is there, which is there one example of such isomorphous system. And if you suppose want to find or use this lever diagram, so suppose C naught is, this will be C naught, and if the C naught is taken as say 35% nickel. So, at this point what you find, so suppose you are taking one portion of this phase diagram. So, what you see is that you will have this line. Now, in this this is your liquid plus alpha zone, and this is your liquid line, and this is your solid line. So, now when you talk about say suppose 35% of the nickel, so you will have 35% here. Now, in this case it will be once you come to any point, So you can have the value of these. So you can, so wherever it touches like this. So this will be your Cl and this will be your Cs. So that way, or C alpha. So this will be your Cl and this will be your C alpha, and at any temperature. So once you come to any temperature which is there on this corresponding to this line, you will have Cl and Cs which is touching at these points, that can be understood, and amount of liquid will be this upon this, and similarly amount of solid will be this upon the whole length. So that way you try to find the the amount of solid which is crystallized at any temperature, and that can be found out. Now so that way you can calculate these values. Now if you come to suppose say binary eutectic system. Now in the case of binary eutectic system, what you see that you have binary means you have copper Ag system we are talking about, and what you see in such cases that your this is your alpha. So this is this being the liquid. So you will have the liquid plus alpha zone here, and similarly you have this beta as the terminal solid solution. You will have liquid plus beta on this case, on this side you will have alpha plus beta which is there in this zone. Now this is the point of eutectic. So as you see that once at this point if there is any solidification, then this liquid will convert to the alpha and as well as the beta. So this is typically for a copper silver system where you get such kind of traits for I mean you are getting this the glimpse of this eutectic point. So as you see here, this is for the 71.9% of the Ag, you are getting this as the eutectic. So this is your eutectic composition, that is Ce, which you are getting at this point. Now at this eutectic point you will have so this is your 8% and this is your 91.2%, and if you have you may have the hypoeutectic or you may have the hypereutectic composition, because the point which is towards the left of this will be having the hypoeutectic composition, and towards the right it will be hypereutectic composition. Now when you are coming to any composition which is at this point, so as we discussed, so once you are coming to any point here, so again you will be drawing a line, and you will have one is alpha precipitating out, and you have liquid of this composition, and the liquid basically so as you come down this alpha you will be the composition of that alpha phase will be according to the point at where you are. So that way ultimately at this point you have this alpha and liquid is of this composition. So you will have alpha, and then ultimately you will have alpha plus beta. So before eutectic point you are getting alpha and liquid, and then at this eutectic point that liquid which is remaining. Now if you look at this point, what is the liquid remaining? So that liquid which is remaining at this point, now that will be converted to the alpha plus beta. So that way in such cases you are trying to have to find out what will be the different phases which are formed at different points. So this is for the copper Ag system. You can have the glimpse of another such system where you have eutectic reaction taking place. You have again alpha the solid solution here for the Pb, and for Sn you will have beta, and this is your eutectic point. So, that is for 61.9% Sn. So, we know that this PBSN eutectic is normally used for the soldering applications. Now, what we see that in this case, if you have this composition, so this it will have the solidification at this point itself, just like pure metal you will have solidification, and that will give you this alpha plus beta phase for this particular composition. Now, suppose if you are told to find for the 4060. So, if suppose you are asked that you find for 40 weight percent and Pb and 60 weight percent. So, that is 40 weight percent Sn and 60 weight percent of Pb alloy, and that is at 150 degree centigrade. So, if that is the case, in that case what you do is again you have to refer to this phase diagram, and what you see is that you are talking about 150 degree centigrade. So, 150 degree centigrade will be somewhere here. So, now in this case, this is your 60% Sn. Now, in this case you are going to have the value of C alpha, and C alpha if you try to find, you will get somewhere close to 11 weight percent of tin. So, you will have C alpha as 11 weight percent of tin, and similarly you will have C beta will be 99 weight percent of tin. So, you can find the relative amount of each phase, and if you try to find the weight of alpha. So, as you know that weight of alpha will be so when we talk about the weight, we are taking into account the lever rule. So, you will have C beta minus C naught. So, it will be C beta minus C naught and divided by C beta minus C alpha. So, that way you can find, and C beta as we understood it is 99, and C naught we have already seen that it is 40% tin we are talking about. So, it will be 40 and divided by 99 minus 11. So, if you talk it will be 0.67. So, it will be 0.67%. So, similarly if you talk about C alpha will be 100 minus this. So, C alpha basically when you, so that is your W alpha, and when you talk about the amount of beta formed, so it will be C naught minus C alpha by C beta minus C alpha. So, it will be again you will find it as 40 minus 11 divided by 99 minus 11. So, it is coming as 0.33. What you see that this is W alpha plus W beta has to be 1. So, once you get this as 0.67 weight percent, it will be W beta will be 0.33. Now, if you take the different temperature, say it was below that eutectic temperature. If you take the temperature, say you are again taking for 40 weight percent tin and 60 weight percent lead alloy, and if you are taking for this alloy at 220 degree centigrade. Now, the temperature is different, and now your 40 weight percent tin will be somewhere here, and you are going to take at a temperature which is 220 degree centigrade. Now, again in this case you have to find the C alpha and Cl, and C alpha if you look at, it will be close to this. So, it will be close to 17%. So, in this case again you will have C alpha as 17% of tin, and if you take the C liquid, now liquid will be 46 weight percent of tin. So, again you can have the relative amount of each phase. So, relative amount of each phase can be found out. So, you can have calculation of alpha phase, as you know that alpha is towards the left. So, you will have the beta point minus C naught divided by C beta minus C alpha. So, it will be C L minus C naught. So, beta is not here because we are dealing with the temperature above the eutectic point. So, you have liquid point only coming out. When we are talking about the temperature below the eutectic temperature, then there was beta phase, otherwise you have the liquid phase. So, C L minus C naught divided by C L minus C alpha, and we have got C naught as the 40 weight percent. So, it will be 46 minus 40 divided by 46 minus 17, and it is coming out to be about 0.21. So, 21% is coming out to be W alpha. So, similarly you can have the liquid percentage, and liquid percentage will be according to the line which is cutting the line towards the alpha zone. So, it will be C naught minus C alpha divided by C L minus C alpha, and in this case you will have this as so it will be 100 minus so 1 minus 0.21. So, it will be 0.79. So, such is the way you calculate these amount of relative amount of phases which are formed in the case of these phase diagrams. Now, you can also you will also come across other kind of phase diagrams which are like you have eutectoid as well as you have the peritectic phase system. So, what you see in such cases you are seeing some points where you see that you have a eutectoid as well as peritectic system. If you talk about the peritectic system, this is a typical copper zinc phase system. You can see that you have gamma plus liquid and it is converted to delta. So, that is basically an example of one solid plus one liquid phase on cooling will give you another solid phase that is formed in the case of the copper zinc phase diagram. Now, in this case what you see, this delta phase, when it will be solidifying below this point, it will give you gamma plus epsilon. So, this type of reactions are known as the eutectoid reactions, and what you see here in this case that this solid phase is converting while getting cooled, it will lead to the gamma plus epsilon phase. So, you will have the eutectoid reaction. So, peritectic and as well as eutectoid both type of invariant reaction is there in the case of copper zinc phase diagram. So, when you deal with such phase diagrams even for non-ferrous systems, typically you see that a lot of such cases appear where you see that you have reaction products. As you come down you will have the different reaction products because the solubility will be different as the temperature is increased. If you talk about the other systems even like copper aluminum system, there also, because on that itself, because when you are in a higher temperature zone, then solubility of one phase into other is more, while when we decrease the temperature the solubility is decreased. So, what happens, the supersaturated phase will again in that the precipitation is likely to occur, and based on that I mean this concept is utilized for exploiting or bringing into the hardness that is known as precipitation hardening. And if so, we can also see that when we talk about the eutectic systems, you may have the solidification or the transformation for the eutectic composition, or it may be for any hypoeutectic composition. So, if you talk about suppose say if you see the PBSN system, which is having eutectic system. So, what we have seen that in the case of PBSN, you have your goes like this. So, you will have alpha here, and then it will be going like this. So, this is your liquid plus alpha, and this is your liquid plus beta. You have beta here, and this side you have alpha plus beta. So, if you talk about the eutectic composition, in this case the eutectic solidification when it occurs. So, microstructural development will be basically normally you will have alternate layers. So, for the for alloy composition, C naught as Ce. So, when it is this is the Ce, so that is your eutectic composition. So, if your alloy is of this composition, in that case you will have a eutectic type of microstructure, and there you will have alternate layers will be there of alpha and beta. So, you will have alternate layers of alpha and beta, that is formed in the case of eutectic composition. Now, if you take a composition which is from here to here. So, if you take say the for alloys which have for which you have the tin percentage, that is 18.3 weight percent tin, and C0 is basically, so the composition will be varying between 18 to 61.9 weight percent of tin. So, in that case again your if you look at, so your so this is your 61.9%, and if you are talking about some composition which is there in between. Now, in this case what will happen, your just if you talk about just above the equilibrium temperature. So, in that case what happens, you will have C alpha that will be coming as 18.3% Te. So, that is tin. So, 18.3%. So, if you talk about just above the temperature, you will have the solid composition as the 18 point, this is your 18.3%. So, this is so if you talk about just above this line, you will have the composition of the solid phase as 18.3%, and just above this line the liquid which is there. So, you will have liquid, and it will have 61.9% that is weight percent tin. So, this is the one. If you come just below this line, so if you go to just below Te, now in that case you have the phases alpha and beta. So, C alpha is again same. So, C alpha will be your 18.3 weight percent tin, whereas you will have the formation of beta now, because just below that you have the solidification. So, the C beta will be again, so here basically your line comes like this. So, this is basically 97.8. So, C beta will be 97.8 weight percent tin. Now, in both the cases you will have if you calculate the W alpha and WL, or in this case W alpha or W beta, that one can be computed, and if you try to compute this, so in this case if you try to find the W alpha, so W alpha will be in this case it will be 0.5, and if you find the so WL, that will be basically 0.5, so just above the TE. And similarly if you go to this case, you will have W alpha, that is 0.73, and W beta it will be 0.27. So accordingly you can find how these microstructures will be changing. So that just be above that you had liquid, and that liquid now so ultimately you will have the conversion from so your composition and this way, and accordingly the fractional volume which is formed, that can be seen using this phase diagram. You can calculate these values. Similarly, you will have the hypoeutectic case as well as the hypereutectic cases, in which you calculate these values of these compositions, and accordingly you can also calculate the weights of such cases. Now apart from that, many a times you will see that you also come across certain phase diagrams where you will have the intermetallic compounds coming into picture. Now this will be normally, if you look at the phase diagram for even the iron carbon system, there also we are not taking carbon as the one which is, so you are not having the carbon towards other side. It is basically the iron carbide, that is Fe3C. So Fe3C basically so you get that as the intermetallic compound. You are getting one intermetallic compound that there will be a line on the diagram, and that also is seen in many cases, and it is normally seen that even the MgPV diagram, in that case you will have the intermetallic compound formed, that is Mg2Pb. So similarly if you look at the iron carbon diagram, here also so in this case the intermetallic formed will be Mg2Pb. Similarly in the iron carbon diagram you get the Fe3C. So in such cases you have you will see that these intermetallics which are formed, and they become they become one side, they will be defining. So suppose at this point in the case of if you try to see the MgPV diagram, what you see that you will have such kind of phase diagram, and then it will go further, and from here you will have this way. So and then it will move. So here basically you are getting this Mg2Pb, and this Mg2Pb. So your basically your this vertical line basically will define on this side. You will have alpha plus liquid. Similarly you have alpha plus Mg2Pb. So basically your all the phases which are taken as standard one from this side. Suppose in the case of copper and zinc, you take copper and zinc on left and right hand side, whereas when you have intermetallic compound formation on the right hand side you have this as the standard line, and your this becomes a phase. So that will be taken into account. Now in this case you will have this will be Mg2Pb plus liquid will be coming, and this is your liquid line. So in such cases you can have the calculation of the amount of these intermetallic compounds also. So then as we discussed that when we deal with other kind of phase diagrams like copper and aluminum, Now, in those cases you will have 1 alpha solution, and then that your solubility will be increased of aluminum in the copper, maybe up to certain amount, and then of copper into the aluminum, and then when the temperature is it is solidified. So, at high temperature it is basically its solubility limit is higher, and when the temperature becomes less, then slowly it will try to diffuse out. So, you will have theta prime phase, that stage is there. So, according to that you will have precipitates coming out, and that is the concept of even precipitation hardening. So, that also is clear. So, based on that you have a precipitation hardenable alloys. You can basically identify by looking at the phase diagrams that which of the materials are basically the precipitation hardenable alloys, where depending upon that formation of the rich super rich solutions which you get, you can come to the conclusion that these are the precipitation hardenable alloys, and they can be hardened by the mechanism of precipitation hardening. So, this is all about the phase diagrams for the non-ferrous materials. You have many systems for which you can refer to the phase diagrams, and that will be utilized for our subsequent lectures when we interact with the materials and its characteristics. Thank you very much.